after we use the maximum internal bending moment to design for the beam, which we choose Y flange W14 by 30. Then we can go to step number 2, which is to check the transfer shear stress. Step 2, check. Transverse shear stress. So the equation from the lesson we learned the transverse shear stress in summer is which is lesson 10. We have VQ over IT. So if you are not very sure about that, go back to that lesson and check. V is the internal shear force, Q is the first moment of outward area, I the area moment of inertia of cross-section areas, and T is the thickness or the width of the beam at the point of interest, at the point we have tau. And in this case, this step, we need to find out the Vmax along the shear diagram. So let's look at here from our diagram. The shear diagram, we see the maximum shear is 40 kips, which can be at point B on the just the right of point B, 40 kips, positive, or point between D and E, which is also negative 40 kips. So they are the critical point, and we'll have the same maximum Vmax is 40 kips. So let's go down here. We can have from shear diagram, we just draw. We have Vmax equal to 40 kips, as you can see, and the I, etc. from the appendix C, from appendix C, where we choose the W14 by 30 is our choice. We can be able to, you see appendix C, standard shape Y flange, and the one we choose is 14 by 30, so it's very down here. And as you can see, they give us the area, the depth, the width of flange, the thickness of flange, thickness of web. For example, the thickness of webs of the 14 by 30s equal to 0.72. So you that take some time to do that with appendix, we can be able to find out the geometrical properties of that cross section. And let me write out in here. We have, from that we have IXX, which is area moment of inertia 291 inch 4, and then we also have T web equal to 0.27 inch, that also appendix C. And then we need to find out Q, and find out Q we need to have at the neutral axis, as you recall in the lesson that we have here for the notes. To do the design, verify tau actual less than tau allowable from the maximum shear Vmax, and add the neutral axis for the cross section that we have. So from here we need to find out the Q, the first moment of outward area from the neutral axis. So let me find out what is Q at neutral axis. And if you are not familiar with that, I suggest you go back to lesson 10 that we have many worksheets working on it. So let me draw that from the appendix C. We can be able to have the half of the cross section of the Y flange, and it's symmetrical, as you can see there. and that is here, and it cut at the neutral axis, so we only focus on that one point. So you can see here, this is the neutral axis. Then we have the depth of this standard shape. From the depth we can divide by 2. We can have the height of that one is 692 inches. Again, all of this information can be get it from Appendix C for W14 by 30. And this the width of the flange is 673. Thickness of the flange is 0.385 inches, and then the thickness of the web, as write out earlier, 0.72 inches. And then we can be able to find out the first moment of outward areas with the equation Q equal to sigma of y bar over a apostrophe. Y bar if from the neutral axis, the when to take to the centroid of each standard shape, and we can divide that into two areas here, the flange and the web. A apostrophe area, outward area, so we can have that here. It equal to a y bar a apostrophe for the web based on that finger plus y bar for the a apostrophe for the flange. And again, we talk about the neutral axis here. So from that, with your geometry, again, you are not sure, you can go ahead to figure out the geometry, and that in lesson 10, I want to make it very quick in here. So it will be, you can 692 minus the thickness of the flange, 0.385. That we have the one side of the web, and we time the thickness 0.27, that we have the area, and it will be y bar is from centroid of the whole shape, which is neutral axis, to the centroid of the web in here. So for that end, that one equal to 692 minus 385. Of course, we divide by 2 because that is the that rectangles. And then we also have the y bar a apostrophe for flange, and in this case that can be a little bit easier. We have 673 times 0.8385, that is for the two sides of the rectangle, find the areas, and then the distance from the neutral axis here to centroid of the flange, and that centroid of flange equal to 692 minus half of the thickness, 0.385 over 2. And from that one we can have Q for NA. Q here is NA. At NA, so we have first component 577 plus the second component 17.43, and total we get that one is 23.2 inch cube. So we have we have V max, we have I, we have T, and we have Q. So we can plug into that equation to find out. So from that we can find out the actual tau max. And at the neutral axis, as you can see, it will get the maximum transverse shear stress. So we get that the critical point 40 kips VQ over IT. Let's rewrite it. Equation Vmax now, because of that Vmax QNA over IT IXXT and T web, because that the neutral axis, the thickness here, the web, not the flange, as you can see there. So from that we can plug in the number 40 kips. QNA 23.2 divided by I, we got there 291. T web 0.27. So from that one we have tau max equal to 11.81 KSI. So that tau max, we have to verify whether tau max less than tau allowable. And you see A36 still, we know what is tau from the appendix. So as you can see here, we have verified design after we find out tau max. So verify or check the design that we have in the step number 1 in here. So we have it tau actual less than or equal to tau allowable, and tau allowable is equal to the factor of safety, as you can see here. So it's here tau max have to be less than tau urine divided by factor of safety. And the problem gives us the factor of safety with regarding to yield is 1.2. We just find out tau y, which is from your appendix number B for A36 steel. And in US customary units, the first line item, and as you can see it shear yield strength for shear 21 KSI. So from that we go back here, we can have one side tau max 1181 less than 21 KSI. This is appendix B for A36 steel. Everyone see that there? Okay. Divide by factor of safety. Problem given us 1.2, which is 11.81 greater than 21 divided by 1.2. It equal to 17.5, which is good. This inequality valid. So we have the first check, first verify of our design, which is the maximum transverse shear stress is okay. So we have that one done, and we will move on to the next step, which is check the maximum shear and moment combination at the web and flange intersection.